In this video, I would like to talk about few basic laws of electrical engineering. First, it will be Ohm's law. So it's named after George Simon Ohm, and the law states that the current between 2 points in a current carrying conductor is proportional to the potential difference between that 2 points, basically. So whatever currents is flowing, let's say potential here is V1, here it's V2, and current is flowing from here to there, I. So I will be proportional to V2 minus V1. So if V2 minus V1 is equal to V, that is the potential difference between these 2 points is V, then I will be proportional to V. And there is a proportional constant, so we can write V is proportional to I. We also can write that, and there is a proportional constant, so this is a linear relationship. So V is equal to, if we want to equate it, the proportional constant is R, which is the law. So that is called the resistance. So R is equal to V over I, that's the Ohm's law, or V is equal to Ri. This is the Ohm's law. This is known as Ohm's law. So this is of course there is some constants there, that is it's the bilateral, the circuit has to be bilateral, so it has to, from this side and this side, it has to be the same. The response will be the same. If the source is here or there, it should be the same in that direction or that direction. So we won't go into that detail, but this is what it is. Between 2 points, the difference of voltage between 2 points is proportional to the current current running through that point, those 2 points, basically. So that's there. Then we will talk about Kirchhoff's voltage law, which comes from basically conservation of energy. So if we have a circuit like this, let's say we have several elements. Elements can be sources or sinks. So sinks can be several types, but we can think of resistance. Resistance is a sink which dissipates power. So let's say something like this, and we have one of them probably a source, and these are probably sinks. I don't know, whatever they are called, VA, VB, something like that, VC, and this is maybe VS, which is the source. So if we start from one point, what Kirchhoff's voltage law says is, if we start from one point, the voltage drop, algebraic sum of voltage drop will be equal to 0, basically. Starting from one point in a closed loop. So if we start from this one and we go through a closed loop, that means we travel through a loop containing elements in the circuit, and we return to that point and we sum up all the voltage drops. We sum it algebraically. So what happens is, in a source there is a voltage rise, and in a sink there is a voltage drop, like that one. So if we go there, the voltage increases in that direction. In a sink it drops in that direction. So if we say algebraic sum, that means we can say the sink is a positive voltage or negative voltage, and the sources are positive and vice versa. So if that's negative, the source will be positive. If sinks is a positive, source will be negative, like that. So algebraic sum will be 0, and it comes from that, basically from conservation of energy law. So we can say that here this is energy created. Energy cannot be created, of course. What happens is, in a source, energy is converted. We know energy can be converted, cannot be created, at least in macroscopic world. In quantum world, according to Heisenberg's principle, which we won't talk about, but there is a in short time energy is created. So that's something else we won't talk about here. But in macroscopic world, we know energy is not created, it's converted. So what happens is, in a source, chemical energy is converted into either chemical energy is converted in electrical energy, like in a battery, or in a generator what happens is mechanical energy of a turbine is converted into electrical energy. So energy is converted. So we can say that energy created here will be equal to the energy dissipated. So if this is Ws, that will be equal to Wa plus Wb plus Wc. So that makes sense, because whatever energy, if we travel the whole path path here, whatever energy was created and delivered to the sinks will be, whatever the sinks have dissipated will be, sum of that will be equal to the energy that was delivered by the source. So this is the energy that source delivers, and these are the energy, the sum of this is the energy dissipated by the sinks. So that makes sense, and from here we can write, we know that V is equal to W over Q from the very definition of voltage, work done to move a charge from one point to another point, 1 unit charge. So basically the algebraic relation was like this: V is equal to W over Q. So W can be written as Q over V1. So charge will be the same here in a circuit. So for continuity, so QVS is equal to QVA plus QVB plus QVC. So we can get rid of the Q's and it becomes Vs is equal to Va plus Vb plus Vc. So basically it's coming from, the Kirchhoff's voltage is coming from conservation of energy law. Now there's another thing, conservation of charge. So the other law is Kirchhoff's current law, which says that if in a circuit we have several branches, say at some point, let's say the circuit is something like this, there's a source and there are a few branches there, and they probably meet up somewhere here, and then they come back here, and there are elements there. So what it says is, at any node, wherever more than 2 branches meet, or more 2 or 3, whatever, because see, we can see that here current is splitted in 3 branches, so that's what it is. So this is, let's say A, this is B. So any node where more than 2 branches meet, at any node, the sum of entering current will be equal to sum of leaving currents. So if currents come here, a current, let's say Is, and let's say this is, I don't know, I have made this, so let's say Ia lowercase a, I lowercase b, I lowercase c. So what it says is 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 equal to Ia plus Ib plus IC. Now in a circuit, what can happen is the source can be here and this can be a sink. There are several arrangements of circuits, and that may result in the current coming in that direction, in the other direction. So that's okay. What happens is, we will just designate current entering as positive or leaving as positive, and we will do the algebraic sum again. So the law actually can be stated this way, that at any node, algebraic sum of entering current is 0 basically. So algebraic sum of entering current means if the current is entering, it's positive, and it's leaving, if it is leaving, it's negative, and then the algebraic sum will be 0. So whatever current is coming, in the end, they will be distributed in several branches and like that. And this is also coming from conservation of charge law, because we know I is given by Q over T basically, like that, Q over T, let's say. So if we have whatever charge is coming here, Qs, will be distributed. So if we have charges related to particles, so if we say electron, now we know that current is by current is created by moving of electrons basically. So let's say we have, I don't know, just arbitrarily speaking, we have 100 electrons coming here. So the charge will be 100 times electrons charge, which is 1.6 into 10 to the minus 19 coulomb. So that will be the total charge, but it will be times 100 electrons. So we can say 100 Q coming here, and then this is very arbitrarily speaking. So let's say 50 electrons going there, 30 electrons going there, and then 20 electrons going there. That's what it has to happen, because they have to add up here to become 100 again, because it's 100 here. So what happens is, the charge will be according to that 100 times Q 100. So what happens is Qs, Qb plus Qa plus Qb plus Qc, and Q we know is basically It. So Is IAT plus IBT plus ICT. So if we get rid of the T's, we get Kirchhoff's current law. So conservation of charge has to be there, because whatever number of particles coming multiplied by the unit charge of a particle will be the total charge. So that actually the total charge is dependent on the number of particles coming, and whatever number of particles, particle won't be destructed into the particle cannot be distributed into 2 pieces or 3 pieces, so whatever unit particle will go. So however many particles are coming, and they will be distributed in several branches, arbitrarily speaking, because that's what's happening, but the number is much more. We don't want to go there, but arbitrarily speaking, if say we say 100, which we have given in this example, so finally whatever charge is coming will be distributed there, and we from charge we get this equation, because Q is IT, again from the very definition of current which I talked about in the previous video. So from there we get Kirchhoff's current law. So this one also, like algebraic sum of entering currents, or we can say leaving currents at any node, will be equal to 0, and that's how the law goes. So yeah.